I'm just saying, you look at where my head is. I can. Oh, there. I see.
Yeah. Oh, hey.
Good morning. Organize this.
Of course. Yeah, everything's looking good?
Yeah.
How's the audio also?
I hear.
Yeah. Great. Now, the thing that I tell people, that's I got a monitor right up there. That's the closest mic.
Oh, okay.
So to you. But you might just have to project your voice.
That's fine. Good to know, though. Thanks.
Do I need to keep it open?
Yeah, if you want now.
Oh.
And yeah, so you don't have to worry about it.
Yeah.
Yeah, I guess. 11 o'clock. Kenton, did you also get the temporary?
Yeah, I did.
Yeah.
Thanks. Yeah.
Okay.
Very nice.
Awesome. So we'll have the meetings with you.
Okay. Yeah.
Oh, yeah. I mean, 3 minutes is always kind of early for these things, but it's nice if there's.
And this.
Yep, that's fine. Thanks. Doing this?
So
Yeah.
we can like.
All right, it's fine.
Remove.
Offices are nice.
Yeah. Really.
Yeah. Applied to do my PhD at ISI.
Really?
Yeah. I work with David Chang, if you
know. I know. I thought they were previously here also.
He was. That's what I applied to work with him, and so then he went to Notre Dame. Like took me with him. So
that's great. So, have you ever been here?
I've been to the office once before,
Oh.
but just for like again. I gave a talk here a couple of years ago, last minute. I happened to be in California, and the speaker was sick, and I just jumped in last minute.
Oh.
So, and I was like, I glued together 2 shorter talks, and it was okay. I was just more like, I was not.
Yeah.
But so you've been here 3 years.
It's not that good.
It is. It's well, it snowed on Sunday. Like so, 4 days ago we had snow, so that's the downside.
Okay.
But yeah, no, it's a nice university. It's a good place to do PhD. It's very good for faculty. I think it's a little less stress than faculty. Really cheap. PhD stipend goes a little bit further than other. Yeah, it is. It's really well known for its vendor.
Oh yeah.
So and they're doing a lot to try and get the grad education better, which is like hiring a lot of faculty now. But it's just it hasn't historically had as much of a graduate focus. So.
Is Kenton great?
Yeah.
Okay.
Okay. Sounds good. Yeah.
Also, you've also been at the Caltech Computing Research Institute. Well, that's not degree because
It was good, yeah.
10 years ago, I heard from my gig.
Yes, well, it's a very exponential scale. So I had a master's degree, which meant that, because it was still paying research, but like the difference between like master's to postdoc was huge, and postdoc to research scientist, so it went up a lot.
Gotcha.
So if you were going to do a non-research position in like just like a developer job, it was a little less paid than that. So I do know, I was talking to people there for a while, that they're having trouble keeping up because oil prices are a little bit lower right now with like the Google, Facebook and stuff right now, because those are offerings. It was good. It was a good experience. It's cool to work on it.
Yeah, I thought it was a great experience.
Yeah, Persian Gulf.
Yeah.
Just like any other CS lab I've worked with. Boss was German.
Okay.
Right. I'm working with a Mexican guy, a Bulgarian guy, a Pakistani guy, right? Most of the people in the office are from India, so quite a few guys from China.
Yeah.
So it's not that different than
It's no more.
yeah. The restroom.
Oh, okay. Yeah.
I just want to make it keep. Are you involved with Lorelei at all, or no? You have to do Lorelei at all?
I didn't do that stuff. So actually, what do I do?
Okay.
From image.
Gotcha.
Yeah, instead of transcribing them first.
Oh, okay. Cool.
Yeah, that was hard. 1.5 year.
Yeah.
And then finally I wrote a paper, but then I submitted the paper like 8 minutes.
Oh, that happens.
I submitted to like ACI conference, but like ACI conference told me like
It's
not a
NLP,
mainstream.
yeah.
But now working on this games, and
Right. Okay.
I feel it's not very
Right.
because
Yeah,
there's a
of
lot of
course. It's interesting. It's good to carve off an area. That again. Right. Very hard to get any paper in the ACL conference. That's how things always work.
Usually they will arrive 5.
Plus, 11 a.m. is pretty early. 11 a.m. is pretty early.
You're working on the
Yes, I was working on it in Qatar also before I started my PhD. Wow. So yeah, well, what happened is about a year into my PhD, everything switched to neural. I used to do a lot of Moses. I still do for some of the Lorelei stuff, but yeah, it went from like nothing to, so then it's like I get like a year into the PhD and everything's neural networks. And I'm like, well, I gotta switch my focus, and everything I know is like so. But that's how research works. So. Feels like quite a few people have moved around while you've been, right? Like Kevin's gone. Left before you got here. Marco is here for like my first year. He's like on one of the Lorelei things now. Were you here when Ashish was here? Ashish Vaswani? So he did his PhD here, and then he stayed on for brain. So, but like he's okay, yeah, because I wasn't sure when he switched to Google Brain because he was here for a while. So. Yeah.
And Martin, and they
right. David left, which was also that's. Did you ever meet Tomer? PhD. Tomer. From Israel. So he was an ISI student working with David, but he was like the last of David's students. So he officially became a Notre Dame, but he still was here now. Graduated like 2 years ago. Hey, how you doing? Good to see you. Yeah, pleasure. Hey, you made it in. How you doing?
Hey, nice.
Welcome. No worries, yeah. Yeah, no, I just a week ago, so working on the lawyer's basis. Wait, really? In the charity classes. But it's like, I know.
Leave the second
I know, but yeah, so. So I was in for 7 weeks with that. It was like removable, but yeah, it's like the sort of work actually. So. Yeah, I'm taking a red eye back. Crashing with her.
Where in the timeline?
She's right on the line with Dennis on right by Rose. Is it PCH? That's yeah. So I think around Rose and PCH. There's a Whole Foods there.
So, yeah, I know where.
Yep.
Yeah, that's not.
Miles, I think. Yeah. So.
we want to learn.
Helps. It's better science. Well, what do you like?
Hey. But actually, a lot of it's, I guess, finals week.
Oh,
So some of
okay.
the students.
Thinking this was more interesting.
Oh, I canceled Lorelei.
Yeah, I saw that. Yeah.
I mean, I didn't want to, but the problem was that I ended up scheduling the Lorelei call and the Natural Language Seminar at the same time. It was okay because we haven't had two Natural Language Seminars this semester.
Oh, cancel Lorelei call.
Yeah.
But we have a dry run starting next week. So
Yeah.
our last try. It's basically going to end up. Yeah, no, I had this very teary. This,
Heartwarming.
Yeah, writing one right now. It's called Malachi. Everything's good.
More? Is it more something?
I actually really didn't want to, but we couldn't come up with a better thing that would. Like, oh, okay. That's the internal name.
Weather here is amazing. We had snow on Sunday 4 days
really?
ago.
Snow?
Yeah. Oh yeah. We always get it in April.
Oh gosh.
Just walking outside, I got a sunburn yesterday.
You not been here much?
I mean, just California, yeah, years ago. But
Wait a second. Did you start? You started? No, you never didn't start here.
I never started.
You started. You were
Yeah.
accepted here and then started when.
Yeah.
But you haven't visited here before.
I visited here actually. I was over Christmas break a couple years ago, and I just happened to be in California. And David was scheduled to give a seminar, and I jumped in last minute.
You mean this?
I think so. Yeah, it was like in December. He was sick, and I just with 2 hours notice came and gave a seminar,
okay.
which was kind of two half talks glued together at the time.
A lot
But
of times that's true, right?
yeah,
Good.
hopefully these are 3 half talks glued together instead.
But intentionally.
Yeah.
What's a thesis?
Right.
Yeah, that's true too. Yes.
I'm thinking late summer, hopefully. It's still a bit, we have to see how ACL posed 4 different things. 2 have been published. Third one is right now, and hopefully the 4th one. Wrapping up some other stuff with David, plus I'm on the Lorelei project. So. Yeah.
Trying to get 3 years. Yeah, ACL. It's cross-lingual information retrieval and summarization thing. So the idea is you have a big corpus of Swahili, and you want to figure out, get some relevant documents for it for your English search terms. So it just retrieves the English. It does a cross-lingual search and then also provides English context. But the search is not, and it's not just translate and then look up. But actually, the translation.
The vector spaces.
Yeah, so slightly more interesting than that. Yeah, it works. It works really well. I've never seen such ridiculous enthusiasm. Like we showed it off to program. I think we weren't expecting it because it's not part of our, it wasn't part of our thing. Like, oh, by the way, we made this demo. They're like, oh my god, this is amazing. We're going to put it on the Twitter feed right now. Like, oh, slow your roll. Hasn't even accepted yet. So, hey, here's the crew.
Yeah, that's fine.
Sure,
I've never seen a seminar ever start.
Yeah, it is. It's finicky. Well, a lot of things that work well are finicky. But you gotta restart them a few times. And there's a lot of other stuff. Yeah, that's true. Yeah, because you get
Even more than
to be a different put out purpose. Yeah, that's true. No, yeah, this was or take your other thing and make it machine translation. Yeah, this is like, well, this isn't a robot walking around a maze, but yeah, it is in a way.
dealing with the output.
Autoencoder stuff that uses reinforcement learning in the middle. The idea being like you have a hard choice to make. This is the speech thing.
Hi everyone.
It's just
To introduce our speaker,
Kenton is a fifth-year PhD candidate at the University of Notre, working with David Chan on methods for improving neural machine translation for low-results and morphological rich language pairs. Prior to Notre, he was a research associate at Qatar Computing, focusing on Arabic machine translation. He was a master's in language technologies from CMU and a bachelor's in computer science from Princeton. Welcome on the speaker.
Thanks. Thanks for everyone coming out. I hear it's finals week, so I appreciate you actually taking time out to see. Feel free to ask any questions or anything during the talk.
Sorry, can we interrupt right at the start real quick?
Sure.
Can someone check in that room? Are you guys set up for presentation? The audio is not good.
We set up a presentation. So
It's set already? It's the panel on the wall, I think.
No, that's
sure
the
which.
presentation button is pushed.
Yeah.
What do you hear?
Okay. It's okay. Well, we could hear you when you were sitting in the audience very well, and we can't hear the presenter well at all.
Don't do that.
Okay.
We can deal. If you've hit the button, I don't think there's anything more to do right now.
Okay, I'll try and talk a bit louder. I was told the microphone's a little far from me. Is that helping?
That is wonderful. Thank you.
Yeah, no worries. Okay. So sorry everyone in the room, I'm yelling a bit, but okay, yeah. So today I'll be talking about learning neural network hyperparameters for machine translation. After a brief introduction, I'm going to jump into some talk about work I have on what I call auto-sizing. Then I'll talk about some hyperparameters for the transformer network, and then I'll talk about correcting length bias. Just to make sure, this is the natural language seminar, so everyone here has some sort of background. So if I say a blue score, everyone's familiar with what I'm talking about? Okay, good. Yeah, I kind of left those sort of slides out, or what machine translation is. So I'm going to jump in and start talking. And so immediately, since I promised you a talk on neural networks, I'm going to talk about statistical machine translation. So back in the day, which is about when I started my PhD, if you wanted to do some machine translation, you could just go online and you could look at like the Moses webpage. And you could clone the Git repository, and there's a really easy tutorial, and you could get it running pretty quickly. There's some Perl scripts. There's a few things, but you would have like a directory to train in, maybe a French and English system, specify that, what your data is. There were some parameters like you might want to use line, row, diagonal, final, and. What if you're going to do reordering or some sort of language model. But if you did this out of the box, chances are you're going to get a pretty good system. And it didn't matter if you're using a French system. There might be some pre-processing you might need to do for an Arabic system, but data sizes, stuff like that, these default parameters would often work pretty well. Same sort of thing, you could maybe do a Joshua system. Same thing, there'd be a directory to train in. Of course, target language, maybe you want to do high-row as opposed to a phrase-based system. Like, again, language model, some tuning data. Nowadays, you could just go on to GitHub and grab something from Facebook AI like FairSeek. Here you'll have your FairSeek train. There's a few different parameters, like you'll have a learning rate that you need to train on. Maybe you're going to do dropout. However, there's going to be like one little difference here, which is kind of this architecture, which are like, here you'll say the transformer. And so there's a bunch of different ones, number of layers, number of attention heads. It could be something else for other sort of neural networks. Like with LSTMs, you'd have different number of layers as well, whether or not you're using GRUs. However, like if you wanted to do something, and this will be straight out of like the code base or the paper, you want to do a WMT sort of data size. They're going to have one sort of architecture. You want to do an IWSLT, it's going to be a different one. And they'll say like, oh, this is your low resource IWSLT one. So if you do something, and this was an IWSLT that they developed for German, and you do it on French, you're going to get a pretty decent blue score. It's going to be just almost 37 straight out of the box for this sort of architecture. However, if you want to do it on what I consider low resource, which is from the Lorelei project, you have this house of English data, you're going to get a blue score of 7.6. So just using stuff out of the box isn't necessarily as easy as it used to be for these things. And if you're actually going to start tuning and look at different sort of architectures and hyperparameters, you can actually get like a transformer system to 19.13. So you're looking at like a 2.5 blue gain, or times for your blue gain there. So you're really, really sensitive to these hyperparameters, and it's not as easy just to use them out of the box. But that's what most people do. I'm going to take a little bit of a step back and talk about this method I have called auto-sizing. Initially talking about some language models. The motivation from this work was when I started looking, okay, I'm moving off of these statistical machine translation systems to the more neural methods, even just some feed-forward ones. You start reading papers in the literature. So you might see something like, we use two 512-dimensional hidden layers. This is Jacob Devlin's ACL best paper from a few years ago, right? Then you might see something such as, we trained a feed-forward neural net language model with the same number of 640 hidden. All right, that one's a little bit odd, or at least 512 is the multiple of 2. This is the Word2Vec paper, right? Where do these numbers come from? The hidden layers were, again, of size 500 and 600. This is a paper by Holger Schwenk from 2007, which was pretty early in the neural for our sort of field. Very nice paper. Later on in the paper, the size of the hidden layers were adapted to the amount of training data between 200 and 1500. Okay, that's a lot to look at. And then my favorite is, right after that it says, we used 1560, which is outside of the range. So when I was trying to get in the field, I'm like, okay, how do I actually do with these? So often when you talk to someone, they might say, oh, we did a grid search, or might even say in their methodology section. So let's say you have a two hidden layer neural network. They might have 200 neurons in the first layer, 400 in the second. Then you train a model, use up a GPU for a day or two, maybe even longer. You get some results, you're like, well, I need to see, how about a 200 and 500? Keep varying that layer, 600, 700, 800, 900. Well, then you can vary the other layer as well. All of a sudden, you're taking up the whole GPU queue and your entire lab hates you. So the problem with this is it's really time consuming. It's expensive. There's no principle behind it. And overall, it really just slows down science. That's kind of the problem. And when you look at people and they'd have a paper, it's either, oh, why did you do this way? And they say, well, this previous literature did this. Or I talked to someone at a conference and they told me to use this value. Right? Again, what happens if you have different data? Or a different problem overall? Why are you using the same architecture? So that's kind of the motivation for a lot of my work. So the method we use is to try and train one neural network and make it so you don't have to do grid search. So we do this by, during training, we encourage neurons to actually be deleted from our network. People joke it's called dropout forever. So here's a zoom in at an individual neuron. So this is what would have in a standard like feed-forward network at an individual layer. During training, what you're trying to learn is the weights of an individual neuron here. And those take some sort of input X, get multiplied by those weights. That's your affine transformation, your WX. Here you're just looking at what would be on an individual row in a tensor if you're going to try and do if you're going to look at it from like a TensorFlow or Pytorch nowadays. And those get summed together basically. So all of the weights get multiplied, whatever the input is, summed together. And the thing is, if you can encourage all of these weights to be 0, what happens is you're now multiplying whatever input it is by 0. So everything is getting multiplied by 0, it is 0, summed together, still 0. And if you're using a nonlinearity where f of 0 equals 0, your output's 0. So nothing actually happens to any of that data. So that would be your hyperbolic tangent or your rectified linear. So here's kind of what a weight matrix might look like if you're going to do your, if you're just going to try and output your tensor right now. You have a weight matrix W. One of these rows might correspond to what is actually getting to one neuron. And the goal is just to try and make that go to 0. How do we do this? Regularization. Most people I think are probably familiar with regularization from just learning theory. So in common sort of regularization methods, say an L1 regularizer, things go to 0, and it would be like individual connections are deleted. So you can see the red ones there basically getting deleted. So you have a little bit more sparsity in your network, but you still have a lot of different connections. The goal of my work is a group regularizer. So what we want to do is encourage all of the connections to an individual node to be driven to 0 at the same time. And then it's as if the node doesn't even exist anymore. So how you would do this, you have your standard objective function for a weight matrix W. We're just looking at one layer. L of W is the negative log likelihood of the model, just standard learning data. But instead of only minimizing L of W, we minimize L of W plus a regularizer. Yeah, this works beyond neural networks, just any sort of regularizer. And R of W can be any convex regularizer. What we look at is sparsity-inducing regularizers. These are like your L1 regularizers, normally what people talk about. So these are regularizer that have parameters that encourage parameters to go to 0. They often have sharp tips if you're going to try and project them into high-dimensional. And they're used for robustness of a model normally, or to reduce the complexity of the trained model. However, what we do is regularizers are kind of messy to play around with. We use proximal gradient methods. So there's a very nice paper that summarizes this, freaking Boyd 2014. Very long, about 100 pages, which summarizes the literature. But it's a more general case of convex optimization. And we use them to do our regularizers. It's a two-step process. So you basically, you do a step where you're trying to objectify L of W, and then you apply the regularizer afterwards. So you're doing it backwards and forwards as opposed to doing it all together. And there's often closed form solutions for this, so it's really nice. And the gradients work out a bit differently. How this would work if you're familiar with like a Pytorch code, what you would see is you do your optimizer.0 gradients. You define your loss function previously, so you do your loss stuff backwards, and then you do your optimizer.step. That would be normally what you do in a Pytorch, like in a Pytorch implementation. All we do is one extra thing, which is like, here's an L infinity 1 regularizer. So it's just one line of code that we add on to it for whatever, here's your linear 1 layer. And I actually do have code that I'm releasing very soon for this. So the experiments on this are done on a 5-gram language modeling. So people are familiar with language modeling, right? Natural language processing is the goal is to predict next word, useful, helpful, difficult, ubiquitous. Right, exactly, right. Or so you just want to give some sort of score over this. So, and for these experiments, we base this off of the neural probabilistic language model. This was first proposed by Benjo et al. In 2003, and then Ashish Vaswani, who was here at ISI, published a paper on this in 2013, and I actually used his toolkit for this. So these have been checked in and are part of the code here. And the goal is here that this would be a trigram language model. These first set of vectors on the left on the bottom would be like the n-2, here's the n-1, and then you're predicting this word here. So these are one-hop vectors. They go through a word embedding, 2 hidden layers, then you have a softmax at the top. The experiments I'm talking about here, I ran experiments where I applied this technique, this auto-sizing technique, to the 2 hidden layers. And I'm just going to report that we did on both. Just this first layer here, which had 1,000 hidden units to start, which is a bit larger than everything else was. So results, here's a 5-gram complexity. So on the right side of the graph, if you have this lambda, the lambda is your regularizer strength. If you have a lambda of 0, no regularizer, this is your baseline. You would see that perplexity is about 55, which was state of the art at the time. And you still have 1,000 hidden units, right? If you did a very small regularizer, like a 0.001, 0.01, something like that, it had the same effect where there's still 1,000 hitting units. That's what the x-axis is. And the perplexity didn't change. However, as we started to increase our regularizer strength a bit, when you got to 0.1, we were deleting almost 25% of the neurons and still maintaining perplexity. What's kind of neat is, if you look at Ashish's paper, he came up with a number of about 750 when he actually did his grid search, and I'm finding 786 to be optimal here. So we're able to do this. However, if you use too strong of a regularizer is always going to impact your model. It'll punish it, and you can delete over 80% of your neurons, but all of a sudden your perplexity gets a lot worse. So overall, we're able to do this. We did a bunch of different experiments, and at least for these V4 and ones, this regularizer strength at 0.1 was very, very consistent across experiments, which was nice. Yeah. Oh, I'd have to remember. I believe this was right around the time the dropout paper was released, so I can't remember if it did naive at the time. All right, this is a 2015 paper. I have some experiments that are more recent that do have dropout, though.
So,
yeah.
With your auto-sizing, sorry.
Yeah.
You're no longer controlling how many neurons there will be, but you are controlling your lambda. Right?
You are, so that's one parameter. So am I trading off one parameter for another? What we argued why this was a win is we were using the same lambda for all of our layer sizes. Okay. So we have one hyperparameter as opposed to, like, here you'd have the two different layer sizes.
Okay, so you do get, so in this paper though, do you end up getting, like you say, like you set lambda to 0.1 and then you layer size this and this?
Yeah,
okay.
So.
What were the two layer sizes?
We started with 1,000 and the other one was, we were using what was kind of standard at the time, that I can't remember if it was 200 or 300, and we deleted a couple from that one, but it was less effective on deleting on the other one, but it was closer to what people were publishing as well. So. Yeah.
So what, just a...
I mean, I guess that's a modeling error. It could be overfitting in training. The training data is one thing, right? So anytime you introduce one of these regularizers, right, it is to try and prevent some robustness to this. I don't know, like, it's very difficult to say why a neural net learns some things and not others, though, all the time. I think it could be kind of how we train it, but yeah.
Did you try starting even higher? Like,
I did at this point, but so all this code was on a CPU. So this is pre-Pytorch, TensorFlow, or anything, so we were more constrained. For like my large-scale models, I had to train this for almost a month. So nowadays, you'd be able to do that, but at the time, we were constrained by resources. On the next slide, I show kind of where we varied the starting size. So this kind of goes to your thing. So 1,000 was the largest we started with here. And so here you'd see if we start with 1,000 or 900, we got kind of converged to the same value there. If we start with 800 or 700, a regularizer is always going to have an effect. It's always going to try and push down on things. That's how a regularizer works. So if you start with like 700, it's going to delete a few, but you can see that slope is not as strong. So, and this is over the training epochs. I feel like I did do a couple experiments where there's a bit larger. I can't remember off the top, and they deleted. I don't think they got quite to the same convergence, but yeah. So it was kind of nice to see that this did have that effect with 1,000 and 900. Behavior during training, again, both of these x-axes is your epochs as you go along with training. This one's just kind of show that the regularizer strength matters. Again, I'm using a value of like, if I use a value of 0 or really small, 0.001, the graph on the left, no neurons are deleted. Yeah.
So apart from choosing the lambda, there's also like parameters to the size of that.
Right. I mean, so there is. What we were doing is we decided to start like, so most papers, none of them are going above 750. But we just decided to use a larger value and see if we could get below it. So like the previous slide, I was showing you that it did have an effect when we tried on different ones. So we're hoping to mitigate some of that concern that you have there. But yeah, as long as you start with a larger one, we've been able to find that it actually works by just, if you start with too small, it's going to not be useful at all. So, but yeah, so this one, if you use kind of the yellow bars on both graphs, if you use too strong a regularizer, it deletes all the neurons in the first step of training, and it can never recover, because once the values are 0, we have them kind of clipped, so they never come out of it. And so the one of 0.1, what was nice is it, again, has this nice smooth curve of how it's training, and you can see perplexity during training kind of tracks the baseline model also. So it's making a smaller model, which is more memory efficient, which is useful, and maintaining perplexity. We're not getting perplexity gains, unfortunately, but we are maintaining the best, like, levels. Yeah.
What's the
Yeah, this is an L infinity 1 for the results I'm presenting here. Sorry, I probably should have said that. In the paper, we have L21 and L infinity 1. These are the group regularizers where we're doing an L infinity over the entire row, which is the individual neuron, and then L1 over all of them, or an L2 over this, a sharp L2, and L1 over all of them. You can also do an L2 over the entire weight matrix, and or an L1 over the entire weight matrix, and it'll cause individual values to be deleted to 0, but you don't get this nice group strength. So, oh yeah, sorry.
Is that better?
Is it better? No, it wasn't. Like you get kind of similar performance, but the problem there is this is nice because you have entire rows which are 0, which means you can delete them at test time. You have a smaller model, right? When you have all of these with just like kind of random sparsity in it, you still have to store the same thing, and it's not giving you any gains there. And here's kind of a picture of our model over training. So after the first epoch, you can see these are your 1,000 neurons, and this is just like we've probably something darker, the value of all of the individual values in our tensor. When things go white, they're actually 0. So you can see over training, things slowly get deleted, and it just kind of looks nice to see this. Also kind of neat, which you don't see so much because this was a feed-forward neural network. It's a 5-gram. You can actually see that the most recent word it was more important to predicting the next word, even though you could see stuff over there. So this is like n minus 1, 2, 3, 4, which was kind of cool to see that you actually got some sort of stratification there. Okay, and yeah, and all of this is in a 2015 NLP paper. We did some MT experiments. Again, this is from this MPLM toolkit, so Ashish should, because this is still before we were really doing the sequence-to-sequence stuff. And the first row there, you see a lambda of 0. This is the baseline, and this is what would happen if you trained a standard Moses system. You get a 23.2. I believe this is a French-English one. We have this neural language model, which was trained with the parameters that Ashish had given us, and you get a 1.5 blue gain. For us, when you do this auto-sizing, where you start with 1,000, get down to roughly the same size as Ashish's, you're getting a 1.4 blue gain, which we did some statistical tests on, and there was no difference between. It's nice to see that you could actually use this method and still get state-of-the-art performance. Questions on this? Almost identical to Ashish's, which was nice. We just start with larger. Yeah, which was really nice to see that we got down to what Ashish had found by grid search. Yeah.
And how was the...
Oh, this was just by adding a neural language model. This is before neural days. So this is no neural language model. This is a standard Moses system with your NLM. And so then you add a neural language model. And so this is basically Ashish's paper from 2013, is this jump here. What we were able to show is we can auto-size and still get the same jump. What was nice. So key takeaways for this method. During network training, we can also learn the size of the network. This reduces experimental costs because you don't have to do all of these different grid searches. It's based upon this group regularizer. And you have to make sure you use a nonlinearity where f of 0 equals 0. So if you use a sigmoid, f of 0 is 0.5, so this won't actually work. So make sure if you're doing this, not feeding this into a sigmoid. And that smaller models can still maintain language model complexity and improve BLEU. I'm going to move on now to talk about more recent stuff like the transformer network. Are people here familiar with the transformer network? Cool. It's state-of-the-art machine translation right now. Again, this is by Ashish, so we take Ashish's papers and I do stuff with it is what I've decided to do. So this is an image from the actual paper. Nowadays, what it is there's no recurrent in this neural network. You'll have n layers, generally like 6. You have an input embedding, where it's going some positional embedding, goes through this multi-head attention, feed-forward network, and that goes through multiple layers, and then the decoder is the same thing, 6 layers. So it's significant gains over a lot of other really, really strong baselines being used everywhere right now. And again, this is kind of what I was talking about at the start of my talk. When you might grab something like the Fairseat code, here's all the different architectures within the transformer that you can use. There's the transformer for IWSLT, for German, WMT, the big WMT data, big French one, transformer for big German WMT. So again, to get optimal performance, you're still having to vary the architecture of this transformer. Or if you look at the WMT proceedings from last year, you would see the dominating majority of the submissions, 29, right, are based on the transformer. with a varying number of encoder and decoder layers. So everyone submitted different size encoders and decoders for transformer to WMT last year. So again, this makes me go, okay, what is optimal? Can we actually learn this? So I'm going to first talk about random search. I've talked about either people saying we did a grid search or we talked to people at a conference and we came up with stuff. There's a little bit more principled theory, and there's a nice paper in JMLR from a few years ago now about doing random search. So let's imagine you have two parameters. This is just kind of a toy example. If you do a grid search over these parameters, you might miss what is actually the strong one because this other parameter maybe doesn't have that much of an impact. So if you do a random search, hopefully you're better enumerating the search space and able to find better configurations with you. So we look at that. So I look at what happens when you do random search of transformer hyperparameters. So this is again based on the transformer from Baswani et al. In NeurIPS 2017. I'm using the FairSeek code, SHADHO, which I'll talk about in a minute for how I implement this. And I'm looking at 4 or 5 low resource language pairs who most of the people in this room will be very familiar with for obvious reasons. And we ended up training over 600 different models on this. SHADHO is a distributed hyperparameter optimization framework. So this is actually by another student at Notre Dame who's created this. And basically, it's a nice way to do random search networks. The key to know about this is how I use this for my experiments. But basically, what you do is you define a base model, M. So that'd be like, okay, I'm doing a transformer. And then you specify in a config file, okay, it can have between 2 and 8 layers. It can have dropout values between 0.1 and 0.5. And then you just kick off something on a CPU in your queue, and it basically sits there, opens up some ports and listens, and then you go to a bunch of your GPU nodes, and you say, hey, I want you to be trainers, and they call out to this head node. They get parameters that have been randomly selected from it. They start training. They return when they have a value, like what's the loss on this, and this keeps track of what the best one is. There's a little bit more complicated stuff on how you can actually optimize on this. I'm just using pure random search. And after you let it train for a little while, it spits out, here's the best configuration for a difference. So here's a table with a bunch of numbers. The key takeaway from this, rather than having to read all these numbers, is how different everything is. So if you look at, I did Arabic to English and English to Arabic, exact same data preprocessed, exactly the same. You can see the dimensions are very different, the number of heads in each layer, the feed-forward language size, what are optimal atom parameters, dropout. All of these things, what's kind of key to see here, we have your Hausa, Tigrinya, some Vietnamese data. All of these, that there's just really not much correlated between them. The one thing that really had an impact, and I did a bunch of like statistical correlation tests, was learning rate. If you choose too big of a learning rate, or really too small of a model initially, it's not going to work. But the rest of them, and this actually is consistent with a random search paper from the JMLR and stuff, is that there often isn't really one set of optimal. Yeah.
So what kind of range is
huge? I mean, so at a certain point, I actually had some stuff where when I first started training, I had, okay, what happens if we do a transformer with 8 layers, right? What happens most of the time is you get a blue score of 0. So then I had to narrow it down because it just was overfitting the training, didn't get really anything on test. But. And also, did you do multiple runs of the same configuration? I did. And I did some once they were stable. No, I did them. I did multiple from different starting conditions. I didn't do multiple runs of the ones that were getting zero. But some of them, right. So I did 5 runs on one of the same Arabic to English, exact same parameters, and I think the standard deviation was blue.
How large of a?
This is Arabic English, which I think was about 100,000 sentence pairs. I can't remember exactly off the top of my head. I have that.
But the Hausa English was Lorelai's Hausa English, right?
Yeah.
You saw like a 2 blue there.
Yeah, the Hausa one I think had a bit more because that was smaller. I did it on the Arabic ones. I don't remember. I think I did some on Tigrinya a little while later, but the Arabic ones are where I did the standard deviation tests on. I think I have the numbers elsewhere, but I couldn't pull them up off the top of my head. I do know that the Lorelei, the very low resource, did have a lot more variance than maybe. I have a table in the paper. I don't think it was 2 even for Hausa. It might have been about 1, but I couldn't see. So I also just kind of reinforce optimal hyperparameters are not universal. Here's the Hausa English, and what I've done is grab what was found in the previous slide, the best parameters for all of these, And you can see what's best on like the Arabic English is going to get you a 7, but the English to Arabic is going to get you a 19. Right? So the key kind of takeaway of this is, hey, look at your parameters. They actually matter. If you have a new method and you have a baseline, are we sure that your baseline is actually strong? So like when you're reading papers, you can be a bit skeptical. Yeah, they're using the default parameters on the Arabic. They're doing the English Arabic. Right? So key takeaway of this, no single optimal configuration. And you should, if you can, devote some effort to hyperparameter search. A little bit annoying to do that. And here I am advocating for one method like auto-sizing that you should do instead. But if you can, you probably still should. So here's some new stuff currently ongoing, and part of it is actually under review, where I'm doing the auto-sizing methods here on the transformer layers. And specifically, for all of the encoder and decoder layer sizes, I'm looking at auto-sizing this. Some of you may have saw a brief 2-minute presentation of this at Lorelei 2 weeks ago. But here I'm applying auto-sizing to the multi-head attention, the feed-forward network in each one, on the encoder, and again, the multi-head attention and masked one, plus the feed-forward layers and all the decoder layers. So here, what we found, and I will point out that the regularizer strength here 10 is a bit different because of difference with batch sizes. This is now a Pytorch implementation as opposed to a CPU. So unfortunately, this is yet another thing like learning rate that is tied to your batch size, it appears to be. So these are L21. So if you do your house English one and you use a baseline system here, we're getting a 13.8. You add this regularizer where I delete 4% of the neurons, I'm getting a 1.1 blue gain. Tigrinya, even though it's not deleting anything, the regularizer is making it more robust in general. Not deleting any nodes, but we're doubling our blue score. Tigrinya is very, very low resource. However, if you're doing the French English one, you are going to lose quite a bit of blue because this has been kind of optimized. This is the architecture size that's been hand optimized towards the IWSLT data. So again, if you've already started and found kind of an optimal one, this can hurt. I am doing this, and I'm just deleting 13%. I am doing this over all the different layers. So I started looking at what happens when you apply the auto sizer to different parts of the model. For instance, if you only do the feed-forward networks in each layer, what's kind of interesting is that you don't suffer as much on the French one, still a little bit. You get even bigger blue gains than everything else. And it has a tendency just to delete everything. And you can kind of see there's actually a residual layer that goes around it, so information is still flowing. But it decided that for these low resource ones that deleting large parts of your network seem to work better, which was kind of odd. And then the most odd one to me is on these low resource ones where I said, what happens if I only try and auto-size the encoder, is I was able to delete the entire encoder and get even better blue gains on these low resource ones. And this is probably because we have 6 encoder layers and 6 decoder, and that's too many layers for most training methods. There's some other work out there from another guy in my lab that's been able to figure out how to train these a bit better. But what's probably happening is the decoder's acting as both an encoder and decoder with this multi-head attention. This is something I'm still starting to dig into, and this is really recent work, so I don't have a solution for it yet. I'm hoping that there's something, but it is kind of interesting that it does have an impact. Oh yeah, sorry.
You're training a language model on the name data and seeing what the blue square that is?
I haven't. I have a feeling that the Hausa one probably wouldn't do that, but
no, not the Hausa.
The Tigrinya, like once you see a blue score less than 10, I'm always suspect of everything. But the fact that the French one, it deleted it, but only lost 2 blue. I don't think that I don't think you're gonna get a 34 off a language model on IWSL.
You have no encoding?
Yeah.
You still have the input embedding, right?
Yeah.
Okay.
You have the input embedding still, so.
Yeah, no.
So it's learning something there. Maybe something's in the embedding or something. Is in the embedding and something is going lower layers of the decoder, but yeah. So I haven't tried that though.
So I think you explained it.
Yeah.
What is the 0 column?
Oh, that one's baseline. There's no regularizer. So that's if you just.
10.
The 10 one is you use regularizer with strength 10. So I have the L of W plus R of W. Yeah, lambda R of W. It's how strong that is. How long?
That is, okay.
Yeah. Yeah, it's the lambda there. Sorry, that could be on that slide. Potentially on this, which I mean.
With some.
Right. So, and like I said, I have a lab mate, Tuan, who many people also know, and he's been very focused on what happens with the normalization and stuff. So it's an open problem we're all kind of attacking different things. experiments, but I don't have any of his experiments included in this. So now the next thing is what happens if you're doing random search? Does it still matter? Can you use this auto sizer? And so this is again on the Tigrinya one. And so the number on the left is your baseline again. There's no auto sizing. The one on the right is we're doing this L infinity one. So overall, I trained 27 different models on Tigrinya here with random parameters. The average blue score is a 5.5. When we did this L infinity one, we were getting about a 0.25 gain. These were slightly statistically significant, but it's I'd have to do a little bit more on this. There was statistical significance over 27, but I haven't done the same parameter multiple times starting, so I'd have to see on that one. Going back to your question from before, on this set of experiments, I have. But if you look at just the bottom, the worst 9 methods, you get gain. The middle third, you're still getting a gain, and the top third, you're getting a gain. And even if you look at the best model, we still got a slight, probably not statistically significant gain. But at least on this really low resource language, we weren't having the same problem which we were with the French one, where it was actually hurting. So what's nice here is that, yay, this method doesn't hurt even if you start from a good configuration.
Size reduction.
I have to remember, so these 27 were over a random search where everything was starting, and so it was all kinds of different ones for each one, and I can't remember off the top of my head. I mean, I think some of them were 2, and I think some of them were even more than 50. So I have those numbers, but I don't have them off the top of my head. But what is nice is that this does show that you can do, hey, this worked well with grid search. It also works well with random. Which is questions I get from quite a lot of people, actually. Not so much in the NLP community, but outside the NLP, they do a lot more random search methods. I mentioned this briefly. I do have a Pytorch implementation of this. I'm hoping to release this next month. David doesn't want it released until the paper's actually accepted, which makes sense. It's a really simple, like you just do a pip install. And it's the proximal gradient methods. So I mentioned there's this Parikh and Boyd paper from 2014 that talks about like a survey of all of them. And I've implemented all of them. And you could do this on any tensor. It doesn't have to be just for an auto sizing. So if you want to do like an L infinity on a weight matrix and it's not in a neural network, it's nice that I have all of this. So hopefully people can start playing around with it and using it for a few other things. I have it running for a few other tasks right now. And so the next thing is I'm talking about NLP, but does this happen outside of NLP? So there was a nice paper in NeurIPS in 2016 where these people did almost identical stuff to us, very similar methods in it. And they did this with ImageNet and VGGB, and they were able to prune 80% of their using very similar stuff. So this does work on other like neural network tasks, which is really nice. So you can see that paper as well. It's got a lot more traction in the vision community. So, but yeah, so it works in NLP vision, and I'm trying a few other things. So moving on to the last part, correcting length bias. So here I'm going to talk about beam search. Again, everyone here is pretty familiar with beam search, I think. Okay, I'll walk through this pretty quickly. Each word in the target vocabulary here is potential translation, exponential search space, running length. So you have to do your heuristic. So here, let's say you have a Portuguese sentence, cachorro puro em cima de mim. And the translation, if you're going to do gritty search, might be the dog jumped over and end a sentence, right? It just stops. And this is a well-known problem that people see a lot in literature. Hopefully beam search, you search more of your search space. As long as you don't have a modeling error, maybe you just have a search error, then wider beam should actually help you. Here, let's beam of 3. You generate the first 3, look at every possible translation from that one, and then you sort what are the 3. So maybe the second one in your beam is already fallen off. The first one's expanded twice. And the one in green is actually the correct translation. So what you're hoping is that if you do this beam search, as you keep expanding over time, that maybe all of a sudden it moves up and is the most likely one and is the top. And so instead of getting this, the dog jumped over end a sentence, you might get a dog jumped over me end a sentence, which is the correct translation. So this is standard beam search. Thing is, this was very, very useful back in statistical MT. You would see beams of 1,000 consistently. However, when you start doing this in neural machine translation, when you make the beam wider, your performance goes down. So this is due to modeling error. It's not a search error. So here we're using log probability space. Kind of toy example here. Let's assume every word that we're adding, the most likely one is just -1 in log probability space. So you start off with 0, you add it, a dog jumped over by the time you get to the end of the sentence, you have a score of -6. Well, longer sequences are going to have lower scores because you're just adding these log probabilities, or you're multiplying the probability if you're not in knowledge space. If you have, like, let's say this is a greedy search, that's fine, that's going to be okay. If you have a wider beam, what might happen is you have this value initially that's really not that high scoring, this -5. However, it never gets augmented anymore. Like, there's no further translation, so the tendency is to generate smaller translations. So all of a sudden, the correct translation, the highest scoring, not incorrect, but the highest scoring is just to start and generate no sequence whatsoever, and it's going to score better than a good.
Wait, so are you saying that the reason that you see more of these, you see a negative beam effect in neural MT, lack of a coverage vector?
Partially, yeah, that's one way to look at it. There is some stuff with coverage vector. That would help.
The
yeah.
general problem is the same. It's
Right.
just that you're never going to get that in MT because you haven't covered.
Right. So there's different ways to look at it. We're going to say it's a modeling error. If you had a perfectly system that was modeled right, again, could you learn something where it automatically learn 0? Like, but I think of it more as a modeling error. But yeah, there is like within the GNMT paper. I think that's the Wu et al. 2016. There is a notion. They do have some coverage stuff in there, and it still helps. But there are some other issues because you could have a coverage where it's attending to multiple words, right? The problem could still exist as a modeling error. But the coverage vector probably would help quite a bit on this as well.
I guess a more general thing to say is that you're much more flexible than what you can possibly generate in
Yes.
the decoder now, and so you're more liable.
Yeah, that's another way to think about
We
it.
still had a link bonus.
Yeah.
Even though that
Right, yeah. Right. Yeah, and I talked about this length bonus a bit, and that was something that the reviewers were like, hey, wait, are we just going back to here, or I need to do MERT in this length bonus all again? Right, so we argue there's a few more benefits I'll talk about in a minute, but the problem, yeah, the wider beam degrades performance. We think of this as a modeling error. I think, actually, one sec. It actually logged me out. Notre Dame, this is on my slide thing there, one sec. No, it's literally Notre Dame's authentication service just decided that.
Oh, because you're doing this on Google.
Yeah, I'm doing this for Google, so I haven't offloaded it. Yeah. Yeah, Wi-Fi looks like it's working down there. Oh, there. Now it decided to go to the next. It skipped ahead a few. Worse things to do. Sorry about that. You know, it is a little Wi-Fi. You've been signed out. Okay, there it goes. I went back in, yeah. And apparently, yeah.
I want to have your slide deck local.
I do have it local as well, so. Yeah. Okay, thank you. I think it's, yeah. There we go. Okay, sorry about that. Yeah, so I was saying wider beam, model error, -5 versus -6. So previous solutions that have been proposed, one is kind of this word bonus that Kevin mentioned. And here you add something to all words that are not the end of sentence, and this encourages longer translations. So just add 0.9 to each of these. They'll get down there. All of a sudden, you're now getting a value of 1.5. So hopefully this fixes it. The other one, which is what you see in most things right now, is length normalization, where you divide by the sequence length. So this is in Wu et al. Also, this is the Google paper, and then Kuhn and Knowles talk about this as one of their challenges. In that one, you just divide. This one is divided by 1, so it's 0.5. Here, you get a -1. If you look at like the Wu et al. Paper, the Google one recommends doing 5 plus the length to the 0.7. Right, again, so these are some parameters that they clearly searched over, and it's like, okay, where does this come from? So, previous solution, add like 12 words, or divide by sequence length, or some modification of it. Problem here, none of these are tuned. So, where are these numbers coming from? Does this work? So, we looked at a method where we did a perceptron tuning. So here you train your model, and here's I have this is actually an LSTM bidirectional one, but it works for transformers. You train the model, you decode on the depth set, and then you compare whatever the length of all your translations are with the gold. And you get this value for your word reward. It's a lambda, and it's a simple perceptron update, which is really fast. Redecode on your depth set, and we were able to do this on 1,000 sentences, so it's very quick. And it'll tell you to take a step in a certain, like, okay, we want to make our word reward 0.2 bigger, decode a few times until you get to convergence. So yeah, the experiments on this tuned reward, here we're doing this on a Russian English system. Yeah.
Sorry, so the only reward you tune for is the
Yes, it's the length one.
Not actually go full mark.
It's much faster. So it is, and this is some other work I've been doing with David for global normalization stuff. Once you start doing all this, you can think about it as training it for using all but one parameter and just learning that one parameter, and it converges a lot faster. Other sort of global normalization methods they try and deal with similar things. So when people do a lot of the other, I think like the Mixer and bad papers, they see that this affects length as well, fixes some of it, but theirs is a lot slower. So ours we're able to do for some of these small beam sizes in 7 minutes. So it's a trade-off. It's in between. With a lot of these things, unfortunately, there's not this amazing one-size-fits-all, but you can go from one side where you don't do any of this to the other side where you're doing full global normalization, full sequence training on everything. And we're trying to say, hey, we can go somewhere in the middle. So this approximates global normalization a bit faster, but alleviates the length. And so, yeah, this was at WMT last year. So here's a Russian English baseline system. You use a beam of 10, 50, 150, or 1,000. In your blue score, you start off with a 24.9, which is decent for this. You get to a beam size of 1,000 without doing anything, length normalization, and you get a blue score of 3.7, which is insane. A beam size of 1,000 was standard 5 years ago in like a Moses. And now here, this is losing you over 20 blue points. And the reason is, for the most part, length. So if you compare this ratio of all your sentence generated versus the correct length, they're only generating 90% of the words. And as you get wider, a wider and wider beam, it's 86%. On down there, you're getting less than a third of the words are actually generated. And this is where a lot of your performance is going. There's still more, and there's future work to be done that shows that if you fix this, it doesn't magically solve MT, fortunately. But that there is that. If you do tune for our this word reward score, you get a gain initially even. So you go from a 24.9, so you get a 1.6 blue gain by actually adding this word reward. And as you get to a wider beam, you still suffer a little on the larger ones. We're not seeing any real gains, but we're not seeing drops anymore, which is nice. And here you can see the reason is our length. We're now generating 98% of the words in the sentences. And that's where our gains are coming. So we're generating sentences that are around the correct length, which is kind of what you would hope to do if you have this parameter. And what is key again, in my thing that I'll just keep like repeating is, there's a bunch of hyperparameters, please tune your hyperparameters. So this is the exact same data, same pre-processing, all we've done is vary the beam size. It's a different lambda value. If you read, so this was actually some stuff that had been done in LambTram, so it's a little bit older. And if you were reading what Graham had said is, at the time he said, use a value of like 0.6, which works pretty well, at least on this. But it varied. For a wider beam, you didn't need as much of one. For a higher one, you did. I did this on, I should say, I don't think I have those numbers before I go to that. I did do this on a French to English and an English to French system. Again, same exact data, same pre-processing. The optimal value for the same beam size for one direction was 0.6, the other was 1.2. And it's not like there was a linear relationship between them if you do it in other ways. Again, these models are very, very there's a lot of these parameters, and it's not necessarily clear why they are what they are. Yeah. Yeah. Yes. And here, this is actually, these are both dev. So here's a Russian English and a German English. This is a beam size of 50. And here I show what happens when you do a grid search. So these are the dev numbers. These were tuned on dev. These are the test numbers. I apologize. So blue score here, if you start with like 0, is smaller. If you go 1 to 1.2, that's too high. Again, it suffers. You're going from about 25, almost 26 blue, down to, you're losing about 4 blue. The vertical bars on both of these graphs are the value that we found from our tuning. And so it's not at the peak exactly because there is a difference between dev and test, but you can see that our length ratio is getting very, very close here, and that our but the different values here are. So the length ratio, if you don't do anything, is too short. If you give this nice word reward score, but it's too much, it's going to generate too long sentences, which are kind of garbage at the end. And again, with the German English, you can see it's 24. All of a sudden, you're dropping down to 18 for this value of 1.2. Like I said, when I did the English to French system, that one, the optimal value was 1.2. So it's not like, hey, just use a value of 1.2. That will lose you 4 blue on one and gain you blue on another. So you do need to tune it. You could do it with this grid search, but ours is a quick perceptron tuning for some of the smaller ones I was saying. Beam sizes, you could do this as a post-processing step in like 7 minutes. Once we got to beam size 1,000, that which took a long time to tune, but.
So,
oh yeah.
So what's the motivation of using a larger beam? Because the neural empty, if you use it.
You get quicker results. The thing is, if you have a perfectly trained model and then like greedy search would work immediately, sort of thing, it's dealing with model search versus the model error versus search error in terms of like learning theory. So if you have search errors in your model, you could have something where you have the correct translation would be the highest scoring if you searched all of your intractable things, but we can't search all of them. So widening the beam, if you have a good model, hopefully would allow you to search better. So. This goes back a little bit before a lot of the neural methods. Nowadays, people are like, just use a smaller one. But again, we weren't really getting much gains for these larger ones, so that's still an ongoing problem. But
You still have not actually gotten a gain.
No, we haven't, which is still a thing. But this is also something I don't think people have actually explored much in the literature. And so it's useful to see that this is, but it also shows that we are able to kind of approximate some global normalization with this search, and that there is other errors out there, that there's some coverage other ones. But.
So I still don't think this solves. I still think there's a mystery here, but
oh yeah.
Correct me if I'm wrong, Kevin, but once upon a time we did try using instead of fixed beams, testing beams, try to get like probability mass. Right, and I remember. Anyway, it was like and I wonder though, like now because everything is piped through a softmax, right? You're much more likely to have a big spike.
Right.
Right, and so you're probably in your top one, you're getting a huge chunk of your probability mass.
Right.
It could be that that's not always the case, and that sometimes you get like some indecision, and that's a good place to have a beam.
Right. Yeah.
So I wonder if having kind of like the beam is like 85%, right? So basically, once you have 85% of probability, you got your beam with some of the cap in there. So.
Yeah, there is, because I do know there's peaks at certain points in it, but I haven't tried. I don't know much literature on this, but it's a good point.
I still don't think it'll work just because you're showing. I mean,
yeah.
You're gonna be up to 1,000. You're getting
right
95%. It's just these crazy bad actors.
Right. There's still a lot of open work here. Like I'd say this is a first step towards a lot of addressing some of this, but
getting into a space where it's just. Right, so you end up saying, okay, if I'm going to take this crazy route, right now I'm in this space. You're never doing any negative training.
Right.
Right. So you have no. You can get like okay, I'm going to take one small step, one bad step, and now I can just generate garbage, and that's all going to have a very high probability.
Right.
So yeah, you definitely have one.
Right, and so what this does is you can take a bad step towards like just end the sentence, and if you've taken a bad step somewhere else, all of a sudden then those are really going to drop down. It likes to truncate. You could, like I said, full sentence, global normalization would help, but this is a quick little fast band-aid apply that is nice, but and here's just kind of a nice visualization of what happens. So this is a histogram of all of the sentences. the length ratios. So this is the ratio of the sentence we generated versus the actual, excuse me, versus the correct one. So these vertical red bars are a value of 1. That would be every sentence was literally generated the exact same. And you can see this nice normal distribution. So the one on the left is baseline. The one on the right is ours, and the one in the center is kind of length normalization, just divided by length. You can see baseline here. This one's nice and peaked with a beam of 10. But it's still at that 0.9 value that I was telling you about. Here, ours are much closer peaked here. As you start widening the beam 100, you can see that these baseline ones start shifting more and more to the left. Ours are still remaining kind of here. And when you get to the beam of 1,000, over a third of ours, I had to actually cut this off, or actually generating no translation at all. But when you get to these wide beams, that's what's happening. Here, on both of these methods, you can see it's kind of the same. Key takeaway, tuning helps. Fast, I talk about this in the paper, depends on the language, it depends on the data, depends on like beam size, BPE, which direction the language is going. So there's, again, no one size fits all. Please tune your methods. If you're going to do some sort of comparison with some sort of baseline, please tell me you've tuned your baseline. You are out there right now, because and I talk about a little more in the paper of how this is related to label bias and global normalization. A little bit out of scope for this talk right now. I want to thank some of my many collaborators. There's so many more that I could put on here, but these are the ones whose work is actually shown on any of these slides. And, of course, the funding agency, which this is supported by the Lorelei grant. Thanks. And any more questions? Yes.
Is there any
Some of the ones, like, are you talking about, like?
There are at least 4 or 5 methods that are using the Bayesian optimization.
The Bayesian optimization. No, that's something that I have to look into now. When I first started some of this work, I wasn't doing the Bayesian optimization, and I know there's like the Bandit one, I think is the Google one, right, that you're talking about? I don't think that one wasn't open last. I think they may have open sourced it now, right? But Hyperband. Yeah, so mainly I started doing a lot of this work before some of these were out there, and it's something I need to look, and it's something that I know my thesis committee is going to ask me about also. Yeah, so at least when I use the SHADHO optimization, so I have some collaboration where I was talking about the random guy, Jeff Kinnison. He made this SHADHO toolkit for random search, which is really nice. And what he's found is these Bayesian ones don't necessarily seem to work as well, because you could have these random sort of things where a random parameter helps more in conditioning on something. It doesn't have the same impact that the Bayesian did in the past.
You have to do warm start and keep them something.
Right, you could still end up in a local normalization as opposed to a global or local optimum versus a global. There's a lot to be done here. I think this is a problem space that like we as a field should be looking at more. I do need to try out some of this. These do look at like months and months of training for a lot of these methods, and I'm more constrained. Random search, grid search, and I do need to try some of these baselines, but I haven't run it. Yeah, I should. Thanks. Yeah. So all the transformer one, I varied the dropout values and tried a bunch of different stuff. I still use dropout in all of these training.
But then when you complement.
Yes. Yeah, people say it is a mock L2 regularizer nowadays, right? Like there's some theory behind it, but yeah, but it's not.
The reason why people, I think a lot of people don't care about the size of the model.
Yeah.
It's like, who cares? But if you care about the size of the model, matters a lot more. The goal is to have more systems.
Yeah. And there's NVIDIA just released a new edge computing neural network device, right? So that one's really constrained the memory. So yeah.
But is that true here? Can you actually put your models?
Yeah, I can. Right now, what I'm
not? But they're smaller, but they're like piecemeal smaller.
20%
so,
on
the
some
things
of
don't
those.
line up.
You can fix on a single machine instead of 5.
I'm just wondering why you get any compression at all, right? Like if it's like I have. If I drop out, if I have 500, let's say, and I drop out like 498 on layer 1.
Yeah.
I mean, number 498
right.
on layer 1, and number 2 on layer 2. still want everything to be just like, you can just.
You can actually, you can save it a bit different.
I guess, yeah.
Basically.
Yeah.
So, yeah.
So, when I look at dropout, if you take the example, and every time you, because it's meant for multiple epochs.
Right.
Every time you see this example, you have to drop out.
Yeah.
You corrupt the same example.
Right, yeah, in a different way.
That the same example,
Right.
you're seeing it in
Absolutely.
a different view, right?
Yeah.
So maybe, but in case of this artifacting, the example remains same.
Right, it does.
It's the same neuron is turned off every time.
That is remaining the same, but like you said, it is complementary to dropout. So dropout is corrupting it. I do think they help each other in different ways.
Can I spell the link?
Yeah.
So this is great work. We looked at links. So our first question is, well, how can I get the link right? And then
Right.
we found that there's parts of the neural network that are devoted to memorizing, counting words, and then
Right, yeah.
searching. And then devoted to making sure that you get along enough things. So we're okay, and that's why that's
Right, yeah.
a reasonable job. And now we're wondering why it doesn't do
Right.
a good job of what you're bringing up. I understand it's really not your job.
Yeah.
You're like everybody else. You call it a modeling error. You
Right.
sweep that one question into the rug, and now we start patching.
Right,
That's
which
the
is.
way we do it, so it's okay. But if you were gonna I guess my question
Yeah.
is why why is the most probable translation?
Right.
Any flyer idea? Why it looks at all this data that looks like this, and then it turns around and says the most probable translation is the MP. Like that's
Yeah.
really unlike the training data that you. How would you?
I'd say mismatch between training and test. I haven't tried this, but if you did a wide beam on the training data after you've gotten very good convergence, would you still see the same? Like that? Right. So if you have overfit your training data, right, would that be a problem? And I'm not sure if it would be as big of a problem then. I mean, that would be my part. Maybe there'd be ways to freeze parts of your model when you understand which parts are doing this. And well, I guess kind of dropout does similar stuff. I don't know. I'd say this is a really fundamental question in our field right now that we don't know. So I wish I had better insights.
Fair
Yeah.
You're here presenting.
Yeah.
Or other, correct?
I am currently running experiments on that right now.
Like what kind of?
I'm looking at some speech recognition stuff right now, and I've been trying to give it to some people who are doing some biometrics and computer vision stuff right now. So, but we're still like, and then there's some stuff with some word embeddings also. It's all very, very, very recent stuff though. So I don't have numbers yet, but it's. My goal is to get this out there, this toolkit release, and let's say, here, let's see what people can do within the wild. Right now, yeah.
The softmax.
I haven't done with the softmax.
The softmax is and if
Right.
you deploy the model memory.
Right.
You reuse the memory. Memory is really depends on the largest.
That's a good point there. At that point, then you're just saying, okay, I want to generate more tokens, right? If you're doing that, or if you're doing BPE, like if you start printing the softmax, like
softmax embedding.
Yeah. Yeah. Right. Looked at that. I need to think about it because if you actually get those to 0, that have the same effect. I see what you're saying. Yeah, I haven't tried that. I need to look at it a bit more. Initially, when I started doing just the feed forward ones, not like the transport stuff, we were so constrained I could only look at 2 hidden layers. Now there's a bit more, but yeah, no, it's a good question. Yeah. Yeah. No, I haven't at that point. Yeah.
Slowly deleting it.
Right, I think it does, and this is kind of what I'm saying. This is like very recent and ongoing questions. I need to explore this a bit more, and that's something just using a language model, but so thanks.
You gotta go to work lunch, but that's
Yeah.
the plan.
Cool, yeah.
I want to
Talk about the
there's something related to it about 2 years ago.
Right, yeah.
Just a different method.
Yeah.
So here's my intern work. But yeah, so I gotta go.
Yeah, no worries.
But let me know if you're probably
Sure, yeah.
here around.
Okay, where is it?
It's in Culver City. So
Okay, yeah, no, I know. Yeah.
I'm gonna see Steve downstairs.
Or I just took my sister's car. That works also.
You drive to here.
I just took a, he's at work.
Okay.
Thank you very much. Yeah, thank you. Very good presentation. Yeah, I think we're meeting this afternoon, right? So, yeah, appreciate it.